Welcome to the Infection Prevention Strategy, or TIPS, Masterclass webinar, Airflow Patterns and Flow Path of Airborne Particulates. Your lines have been muted, but if you do have a question, look for the Q&A icon at the bottom of your screen and type in a question. We'll do our questions at the end. If we can't get to your question, we will gather the questions and follow up later. My name is Dan Mueller. I will be the moderator for today's webinar. I'm with Garcia Medical. I'm also a TIPS board member. By participating in this webinar, you acknowledge that the statements and information provided is for general guidance purposes only. The coronavirus situation is evolving and dynamic. You are advised to contact your local government and regional health authorities for specific instruction on all topics mentioned in this webinar. This webinar is not to replace the guidance and authority direction of your local government and health authority. TIPS is a non-for-profit organization existing to advance innovations, ideas, and processes which make a difference in global health. TIPS extends to over 30 countries and is the key strategic partner for many notable organizations, initiatives, and events. In the past few years, TIPS has contributed millions of dollars worth of scientific impact through various programs. Our motto is join, contribute, make a difference. You can learn about their successes several ways on their open access journal at infectioncontrol.tips, at conferences such as the HITS conference, through masterclass events at masterseries.events, or on their podcast series. Visit the TIPS resource page for the most up-to-date information. You'll find such information as articles on coronavirus, links to global resources, Q&A from webinars, and links to previous webinars. Today's webinar is sponsored by Swantech Energy Solutions, providers of UVC air treatment units, UVC robots, intelligent UVC lights, and intelligent UVC keyboard cleaning units. The webinar series is also sponsored by Garcia Medical, manufacturer of NADCC, fast dissolving disinfection tablets in water. This surface disinfectant is used across the US and globally, EPA approved sporicidal, and also for emerging pathogens, virus, SARS-CoV-2, and biofilm. We want to get you to know the audience a little better, and I think you should see a poll come up. If you could, this is an anonymous survey, just plug in what your role at work is, and that'll give us a little more information for our presenter. Thank you. So a good wide range of attendees. I've listed out the learning objectives if you want to review those. Without further delay, let me introduce today's speaker. Dr. Konkari provides engineering solutions and insights through physics-based simulation and computational fluid dynamics, or CFD analysis. Kishore has years of experience in providing CFD consulting services, which lead to optimized solutions to a wide variety of engineering problems involving fluid flow, heat transfer, mass transfer, and other similar engineering processes. A noted expert in CFD, he's been regularly published in technical journals and trade magazines. Kishore is an ASHRAE Distinguished Lecturer and recipient of the ASHRAE Distinguished and Exceptional Service Awards. Kishore?
Thank you, Dan. I appreciate your kind words here. Let me share my screen. Can you see my screen, Dan?
Looks great.
Very good. Hello, everyone. Thanks for joining. Today, I'm going to talk about all about airflow patterns and how these airflow patterns impact the flow path of airborne contaminants. The world is going through pandemic crisis. Our humanity challenged, our innovativeness, our ingenuity, everything is at stake. And definitely, we as a human race, we will come out of this. So, with that background, I think this topic is particularly important, uh, considering how the airflow patterns affect the spread of contaminants. And I'm going to talk in general terms here. There are references to COVID here, but what I want you to learn from my presentation is high-level principles. What you will see, the applications here may not be directly applicable to what you are doing, but you can learn the high-level principles and apply it to your situation. So let's start with the purpose of ventilating the buildings. Why at all we supply the air to the buildings? And the most important, the primary objective is to create comfortable, healthy, and productive work environment for the people. Remember, buildings are for people. And while doing that, we try to minimize the infection and hazard due to airborne pathogens and toxins. So those can be viruses, bacteria, chemical vapors, and so forth. So that's our primary goal. And we want to make sure how we achieve this goal through the proper design and optimization of our ventilation systems. So these are the three pillars, as you see on the screen, are the ventilation strategies in general. Containment. So we try to pressurize the spaces in such a way that these airborne contaminants either do not leave the room or do not enter the room. So that's the containment, and I will talk in more detail about it. The second strategy that probably most of you know is dilution. You supply clean air to the space and try to dilute the contaminants into the space so their effect, especially in terms of exposure, can be reduced. And finally, once you supply the clean air, it meets the sources of contaminants and the clean air gets dirty. We need to effectively remove the clean air from the spaces. This part, the removal part, is very closely tied to where you supply the air and how you take that dirty air out from the space. This is often overlooked. People think removal is not a big deal. I mean, I just throw the exhaust grills in the space and make it a day. So it doesn't work like that. So there is a science behind it, how air moves. So let's talk about the containment, the room pressurization. So when you supply more air to the space and take less air out from the space, what happens is you effectively pressurize this space as positive pressure, because that excess air that you supplied, that you are not taking out from the designated exhaust grills, goes through the door undercuts, the gaps in the walls and ceiling and so forth. That air does leave the space, but it pressurizes the space positively. So if you don't want any outside contaminants to get into the space, then you positively pressurize the space. That is like operating room. You don't want outside contaminants to get into the operating room, which will eventually may deposit on the surgical side. The other part of it is negatively pressurized rooms, where you supply less but take more air out. And that deficit of this between the supply and the exhaust comes from the outside. So basically, the air from the corridor will enter your room, like in isolation room, where you don't want the pathogens or germs to leave the isolation room. You always want the outside air to enter the room. So that's where you negatively pressurize the space. This is very common in healthcare facilities, like operating rooms, isolation rooms. Not so common in office spaces or restaurants or even dental clinics, if I can extend that. One thing to remember that these pressurization techniques work only when the door is closed, when you have a confined space. As soon as you open the door, there is a bidirectional flow of the air. So outside air comes in and some part of the inside air goes out. So that pressurization fails with the open door. So there is a lot of talk about pressurizing the spaces. And if you have a frequent closing and opening of the doors, like a restaurant, office spaces, waiting lobbies, pressurization techniques is not going to work simply because the door doesn't remain closed for most of the time. So this is about pressurization. Remember, these pressurization techniques treat the space as a black box. It doesn't care what is happening within the space. It is the zonal transport, the transport of contaminants from one zone to other, from corridor to the room, from operating room to the maybe the anteroom or the buffer zone you have. It doesn't talk about what's going on into the space. Okay, so that I'm going to show it to you shortly. Let's talk about the dilution. You supply outside air, supposedly mostly clean air, to dilute the concentration of the contaminants in the space. And we often call air change rates. Basically, if Q is your supply airflow rate and you divide it by volume of the space, you get air changes per hour. The unit is 1 hour. Okay, so that is air changes per hour and air change rate. Most of the time, people think air change rate is like how many times the room is exchanging the air with outside. It doesn't work like that. It's not a piston effect, like you just push the air in one direction. Once the air comes in, it circulates in the room, probably stays a little longer, and then leaves the room eventually. But it is not necessarily a very linear exchange of the outside air with the room air. Now, how to determine the dilution concentration? Very simple equation. If you know the generation rate of the contaminant and you divide it by the supplier flow rate, this is kind of a well mixed, if you will, concentration in the room. So how the concentration, how the dilution works with the air change rate. So if there is a contaminant source, it starts polluting the room, and then the concentration goes on increasing. And let's say the patient leaves the room here, or somehow you stop the contamination there, And this concentration will deplete with time. So this is the ramp up phase here, a steady state phase, and the decay phase, or the purge time here, the purge phase. This is especially important now. There's a lot of discussion how long the cleaning staff should wait to get into the room once the COVID-19 patient leaves the room. And this is where it comes into picture. So you can think about this like patient gets into the room and the concentration of pathogens, if you will, keeps on increasing, and once the patient leaves the room, it goes down. So how the air change rate works? Like higher the air change rate, as you increase the supply airflow rate here, your dilution increases. So your concentration goes down as you increase the supply airflow rate. However, this is with diminishing returns. It's not like you keep on putting more and more air in the space and you will get linear dilution. It doesn't happen like that. So basically there is, after some time, after some level of air change rate, you will not see its effect as you can see from 4 to 6 or 6 to 8 for that matter. As you can see from 8 to 10 air changes, that diminishes. That is one thing. Try to understand the difference between the air change rate and supply airflow rate. The supply airflow rate is the quantity that determines the level of dilution. And air change rate, when you divide that supply airflow rate by the volume of the space, it determines the rate of buildup and purge that I explained it to you. So try to differentiate between the supply airflow rate and air change rate. So volume of the space specifically acts like an inertia or a flywheel effect. Larger the room, it will take longer time to purge and so forth. So all these equations here, they are developed quite a while ago, few decades ago. And that time, advanced techniques of analyzing the airflow were not there. So all these techniques assume it's a well-mixed condition. A well-mixed condition, it means it's like just like your coffee cup and you are pouring the cream in it and stirring it and creating a instantly homogenized mixture. It never happens in any space in the world. So this assumption that the spaces are well mixed and instantly they will give you the uniform concentration, it's a myth. If at all it works, it only works in your exhaust duct where we don't live. We live in the space about 4 to, and our nose is about 4 to 6 feet height from the floor. So this is about dilution. What about removal of dirty air? And that is very much tied to airflow patterns. You want to remove that dirty air as efficiently and as effectively as possible. You don't want your supply air to short circuit the room. Supply air, once it comes into the room, it should do its job of cleaning. And you don't want that dirty air to stay there like your unwanted guest, those who want to stay forever. You want to get that dirty air out as quickly as possible, as efficiently as possible, without making any harm or damage to the other spaces of the room. So the location, number, and type of supply diffusers, they affect the airflow patterns. Your supply airflow rate, as just we talked, that is related to discharge velocity from your diffusers in the space also matter. Location and number of exhaust grilles in the space, that can affect your airflow pattern. Location and extent of heat sources, like human beings, we generate heat, we give away heat. Your computers, lights, all those heat generating entities create the heat, and then hot air goes up. But that creates this buoyancy effect and affects the airflow pattern. locations of contaminant generation. So how many places you have the source of generation and at what rate they are generating the contaminant can affect how they spread in the room and how effectively you can clean the space. Of course, the layout of the facility, how your furniture is laid out, where the dental chair is, if it's the office space, how the cubicles are arranged, how tall the partitions are. All those things matter because those are all obstructions to airflow. Obstructions to airflow. So if you create large obstructions to airflow, the air may get stagnant and create a stagnant zone or dead zone, or it may just circulate there like spinning the wheels. And if the contaminants are caught in that circulatory zone, they will stay there for a long time. So these are some of the factors that can affect the removal and airflow patterns in the space. So why airflow matters? Air is the primary carrier of heat, moisture, and all airborne contaminants. And therefore, understanding the flow path of air is key. It's key to your ventilation, it's key to how clean your space is, it's key to your thermal comfort, and it is key to your health and well-being and productivity. So that's why airflow patterns play an important role. So as I said, airflow patterns determine the speed, airspeed in your space, whether you are creating drafty zone or stuffy zone, the distribution of heat, whether you're creating cold spot or hot spot, contaminant flow path, where all these contaminants are accumulating and where there is a low concentration zone and high concentration zone, and our thermal comfort, how we feel, whether we feel too cold or too hot or just comfortable, depends on air movement around you and airflow path in the space. And finally, the effectiveness of ventilation. Effectiveness of ventilation. It is not just how much air you bring in, how well that air does the job of ventilating the space also depends on airflow pattern. And yet, we cannot see the air movement. All of you, look around. You cannot describe where the air is going around you in your room. You probably can point out to us a diffuser, probably from that's where the air is coming in, and you may know probably where the air is going out. That's it. You don't know anything in between. And that's the power of science that helps us to visualize the air movement. So our engineers and architects, they're good in drawing arrows on their drawings. They draw even colorful arrows. They sometimes put the wiggle on the arrow just to show air movement. Well, that is our intent of air behavior. That's how we want air to move. It's a wishful thinking. I mean, air has its own mind, and we have to get into air's mind to understand what air will do. And for that, I have some common sense laws of air motion. You don't have to go to engineering college to learn this, and probably you experience this. Air takes the path of least resistance. Air loves to take shortcuts like we do. If there is a traffic jam on highway, you don't stay there. I mean, you try to find your first exit, get out of it from that crowded space. Air does exactly the same thing. It tries to find the nearest exit to get out of the space. Hot air goes up like a helium balloon. And that's why we can enjoy these hot air balloon rides. Hot air goes up. It sticks to the ceiling like a helium balloon, and it doesn't come down on its own unless you pull it. So that's very important. So if you have a hot air in the space, and if you're generating the contaminants in the vicinity of your heat source, those contaminants, airborne contaminants, will ride the wave of air and it will go up. It will go up. So try to remember that. And then cold air always stays near the floor. if you complain, cold feet, especially in a cold climate where I am in Ann Arbor, Michigan, we know why our feet are cold. Cold air is heavier, just like hot air is lighter. It stays to stay near the floor. So if you have a cold air and that is sitting near the floor, it is possible that your airborne contaminants may stay near the floor. Okay. So these are common sense laws of air motion. Well, we don't have to depend on these common sense laws. We have to go beyond that. And there is a science called computational fluid dynamics. What it does, it simulates fluid flow of air, water, other fluids, even mercury, blood, whatever fits in the definition of fluid in fluid mechanics text. It can simulate fluid flow. It simulates heat transfer, heating, cooling, effect of body process, solar heat gain, and so forth. Mass transfer, like movement and transport of water vapors, gaseous contaminants, airborne particulates, airborne viruses, and whatnot. And of course, chemical reactions sometimes. The fire simulation, if you want to know how the smoke moves in the case of fire in your space or in an atrium, you cannot do the experiment. I mean, you cannot put a sofa from a junkyard and put it on the fire just to test your smoke exhaust system. There is no other way but to use computational fluid dynamics to understand the effectiveness of our smoke exhaust. How CFD can help us visualize airflow patterns. As I said, that's the biggest part. That is unknown. We don't know how the air is moving. If we don't know how the air is moving, we will not know how the flow path of airborne contaminants are. If we have a source here, if somebody is sitting there and there are virus particles coming out from somebody's breathing or sneezing or coughing, we have some high-level guidance, but we don't know exactly where those airborne particles will go. That's why it predicts the low and high zones of concentrations. Also the drafty and stuffy zone, hot and cold spots. We can identify the risk. Where is my risk? Is the air moving properly? If it is not moving properly, am I going to contaminate the space? And which part of my space will be contaminated? And then we can use this knowledge of air movement to mitigate this situation if there is a problem. Where can I place my supplier? Where can I place my exhaust grills and so forth? And it takes out the guesswork from your design, from your understanding, and you have a microscope placed on your space to understand how air is moving, where my contaminants are going, and then basically it avoids expensive trial and error efforts. Those who are in building industry, they know retrofits are very expensive, very frustrating. So these things can help us properly design the spaces and mitigate the issues related to airflow patterns. Let's talk about particle dynamics. You can see a picture here. This is the worst case scenario. This guy is coughing here, and in the cough material, there are droplets, large droplets, small droplets, and aerosols, those who get airborne. So large particles or droplets, they fall near the source, where the source is. You can see these are the heavy, large particles are falling close, and that's where our 6 feet social distancing guidance come into picture. Remember, that is for the still air. If there is a wind blowing, that 6 feet may not be the appropriate guidance, okay? And then the particles which are smaller than this large, heavy particles, they will just fall close to the source. And the particles generally which are less than 5 microns, they ride the waves and then they go with the with the air. They travel further. So aerosols, they follow the flow path of air. They just like a roller coaster. They just enjoy the ride with the air. The particle density, their size, their shape, all that can affect the dynamics of how particles move into air. One thing to remember, these large droplets can evaporate and they can become airborne. So depending on the temperature and relative humidity and airspeed around the source can determine how they evaporate and whether they can become aerosol and airborne. External forces can affect this trajectory. Uh, the good example is the gravity. That's why these heavier particles, large particles are falling down. Buoyancy, just now I explained it to you that if there is a buoyant force and the hot air is moving up and you happen to have that source in that vicinity of the hot air, these particles will also rise with the air. Let's now talk about few examples here. In the objective, it was mainly emphasis on patient room, but I'm going to show you a couple of other examples here. So this is a patient room here. The patient is lying on the bed. There is a caretaker here. There is a sofa set for relatives to sit. There is a TV for patient to enjoy the situation in the patient room. There is a computer here. So for ventilation, of course, there is a large window here, and the sun may come through that window and can make the room hot. There are two supply diffusers. We call them linear diffusers, like a slot, and they throw the air on the hot window there. And then we have one linear diffuser here, another slot that will supply the air to the room. And then we have two lights here. By the way, there is a small grille, exhaust grille, or return, what we call it, to take the air out from there. Again, there are no set guidance how large this grill should be and where it should be placed. Contractor goes and starts building this hospital and say, oh, wherever it feels good, wherever it looks good, just throw that grill there, okay? And then, of course, there is a door leakage. As I told you, the air can come in and out from there. And of course, there is a bathroom attached to this patient room, which I have not modeled. And then there is a bathroom exhaust fan, which will pull the patient room air into the bathroom. Okay, so these are some of the components of this model here. Let's look at the airflow patterns. Now, this is where our visualization comes into picture. You can see this air sweeps the window there and tries to come here. And this air moves along the ceiling, strikes the wall here, comes down, and then it just circulates. After some time, it's just a colorful spaghetti, if you will. At this point, it's hard to know what's going on. But here, at least you will see the air motion, and this spaghetti is colored by the temperature of the air. Now, we can simplify that. And if I take a cut plane passing through the patient, this gives me some idea. This air is moving up here and then moving along the ceiling, striking the here. And oh, look at that circulation zone here. It's forming a large recirculation of the air at the footboard of the bed. Now, look at the temperature distribution. What's happening is these pumps there and this person and the patient and the hot window and the TV and computer, they're generating the heat. So as this air moves over the patient, it picks up the heat. And you can see heat can accumulate here, but the cold air is coming down here and it's kind of creating more or less comfortable environment for the patient and the caretaker. What happens to the flow path of aerosols? Now, this is critical. When these aerosol particles are generated from patient's face, they travel upward and then they get caught into the supply air stream, and then they just enjoy their ride with the air. They are just moving and getting there and circulating round and round, round and round, and eventually they are finding their way out. These aerosol particles, they are not finding the path of least resistance, okay? And in fact, my slot diffuser is acting like a germ spreader here. Uh, they are not readily finding, hey, how can I get out of this room? Why is this happening? See, most of our spaces are designed by the diffusers. They have, we call it induction methodology or inductive diffusers, mixing diffusers. The idea is when you supply the fresh air, clean air, it should mix quickly with the room air so that the fresh air reaches the occupants readily and uniformly. Well, it also acts for mixing the contaminants, as you are seeing there. So in this case, you can see that jet of high velocity air coming out, and then it is creating a low pressure zone, and it is inducing the room air with it, and it is circulating there. So most of the diffusers you see in these spaces are either four-way diffuser or slot diffusers, and they have their purpose. So how can we mitigate this situation? So what I thought, instead of having this two small grill here, why can't I place a large grill right behind where my supply is, and see if I can create a path of least resistance for these germs to get out. And let's see what happens now. This is the airflow pattern now, the new airflow pattern. All the air is now trying to go towards that exhaust grill, and it's following that flow path, though there is some recirculation in the room that is there. It comes with the air movement. But and then this is the new path. As you can see, all these arrows are pointing towards that grill there. And what happens to the aerosols? Now, it's almost like a magic. These aerosols, these particles, as they go up, they say, hey, here is my exit. I don't have to go anywhere else. Just like we do. Once we are driving on highway, we find our exit, we get out of there. We don't go 10 miles down and then take a U-turn and come back. We take the first exit. These particles are doing the same thing. They are finding the path of least resistance. You may ask, will it work exactly like that in real room? Probably not. But if you compare between the two designs, this design shows a lot of promise. And therefore, if I have to design the patient room, I will design it like this, because it is providing the path of least resistance without hurting the other aspects of the ventilation, the thermal comfort of the occupants, and so forth. Okay, so I'm not going to get into the details of thermal comfort part because that's not the emphasis of today's talk here. Let's take another example of laboratory ventilation. You may say, oh, why I have to do what I have to do with laboratory? I don't work in laboratory. But as I said before, take this principle, look at it from high level, and try to understand how contaminants move into the space. So these are the benches in the laboratory. You can think that as a cubicles. You can think that as the walls of the cubicles and so forth. So I have 3 four-way diffusers, as I showed it to you. Those are most common in most of the occupied spaces. I have 2 exhaust grills here. I have 3 persons working here. And there is a source of contaminant in front of this person. Let's assume this guy spilled a bottle of chemical and it starts evaporating from there. So what we are going to do, we are going to look at how that contaminant spreads into this lab space. Let's look at airflow patterns. These airflow patterns are very complex. They are not just like what you draw on your drawing. I mean, the air is moving along the ceiling, and if there is an exhaust grille, it will escape from there without doing its job. But then rest of the air is creating a lot of circulation zones here, around here. So let's look at the flow path of contaminants. And you can look at this as a fog of contaminants. They are released from this person's table here, and see how they are spreading. They are mostly going in this direction. Maybe this grille is close to this source, and it's trying to find way out from there. And once the source stops, it purges the room. It cleans the room. So we are injecting the contaminant for some time, and then we say that all the liquid is evaporated, so there is no more source of the contaminant, and now it is spreading into the room. Look, there are few contaminants here compared to this part of the room. What is important in occupied spaces where we live and work is our breathing zone, where our nose and where our mouth is. That is generally at 4 to 6 feet high. So if I take the cut plane at the 5 feet height and look at what's happening in that plane, what you're seeing here is that it's now in the purge phase. The fresh air is cleaning, sweeping the contaminants. But once the contaminants start generating, you see how that high concentration zone is moving around the benches, around the people. And this guy, the poor guy, head is completely immersed in that red color being the concentration, high concentration zone of the contaminant. We can look at this as a cloud. What is this cloud? This cloud is the zone of concentration, which is at unacceptable level. So if that is 25 ppm, then everything under that cloud, inside that cloud, is about 25 ppm. So if the acceptable level of concentration is 25 ppm, I can see where my dirty zone is and how it is moving with time and how long it takes for me to clean my space once somebody spills that contaminant on the table. You can think this as an office space or a dental clinic or ophthalmologist clinic or restaurant. And if somebody is coughing, sneezing, or even breathing, a asymptomatic patient, then where that all cloud is going to go, and that will depend on the local airflow patterns of that space. And you can see when this cloud gets trapped between the cabinets, if you have a stagnant zone, whether it's under the table, between the two cabinets, or sometimes between the two beams near the ceiling, when the contaminants, they get trapped in such spaces, they are the last one to leave the space. Air cannot find them. They're hiding behind those cabinets. And so air has to do extra work to push them out of that space. Okay. Let's look at the concentration levels. As I said, breathing zone is the critical zone. And now if I put the sensors in front of their nose here and see what the concentration they're experiencing with time, look at this. Person 2, who is not even, person 3, who is not even closer to that source, is experiencing the highest concentration. And of course, then the person 2 and the person 1, who is away in that corner, is least exposed to that contaminant. And I can even compute the exposure, the dose of this contaminant. You can see it keeps on increasing. And of course, when the contaminant source stops, when the patient leaves the patient room or the person who is infected leaves the restaurant, this is the exposure level of the rest of the people. So you can see the person 3 has highest exposure because he's close to that grille compared to person 2 who is even close to the source. Okay. So if I have to mitigate this situation, if I can add one more exhaust grill, do nothing, exactly same space, don't add any more air, it makes a difference. You can see here, the red color is limited to this zone. If you see the animation here, this red color is not spreading into the room, but mostly confined to the central aisle of the space. Look at that blob at the end of 12 minutes. What I'm seeing here, it is occupying almost 27% of the room. When I put one more exhaust grill, my design engineer told me it costs $500 to put that extra grill. I can reduce that spread by 16, reduce it to 16%, from 27% to 16%. Significant improvement simply by adding one more exhaust grill. And this is the animation. You will clearly see that red blob is not moving towards that person 3. Rather, it is staying in that central aisle away from the occupied zone. Try to note that. What happens to the exposure dose? You can see here, this is with the 2 grills and this is with 3 grills. Significantly, the exposure level has gone down. What we did, not a rocket science, we created the path of least resistance for contaminants to leave the space. And just by adding one more exhaust grill into the space, what happens to person 2? Same thing. We have significantly reduced the exposure. And for person 3, it is very significant. You can see by just adding one more grill, we can reduce this person's exposure significantly. Well, some of the things we can do now is the airflow assessment of the space, the design and layout of your HVAC configuration, effectiveness of airflow management devices, airflow patterns and flow path airborne pathogen, what mitigation strategies we can take and how to implement that. So nowadays there's a lot of things in the market and there are different levels of claims about the cleanliness. So what is important to understand, what is the capacity of such devices, where their locations are, where is the optimum location, what is their capture efficiency for airborne contaminants, and how the local airflow patterns will impact the effectiveness of such devices. Again, assessment of airflow patterns is important. That will tell you the flow path of airborne pathogens, and it will help you understand how to mitigate situations. Okay. Optimizing the social distancing, again, 6 feet, we are just following 6 feet, but 6 feet under what situation? We have to understand that. So if we are social distancing people, then what are the local airflow patterns? Do we know how air is moving? So simply 6 feet distance from person to person may not be effective. That is effective only for droplets, may not be effective for aerosols. And we may need different strategies. Control the source. This is the ANSYS company did this simulation. Wear the mask. That's the best strategy we have now. Because if you control the release of contaminants at the source, our job will become easy. What we learned today, airflow patterns determine the flow path of airborne contaminants. Location and number of supply diffusers and exhaust fields matter. Just increasing the ventilation rate is not enough. You can add another air handler, another blower in the space. Unless you understand the airflow pattern and flow path of contaminants, just adding more air would not help. just increasing the filtration and adding cleaning devices are not enough. Where these devices are, what are their efficiencies, and how the air is moving into the space. Remember, filtration can filter the air and provide you the clean air. How that clean air gets dirty and where that dirty air goes is the key in protecting the people. Finally, CFD, Computational Fluid Dynamics, is an effective tool to optimize the flow path of contaminants, as I demonstrated to you. So with that, I can take few questions. Dan, we still have time?
Yes, thank you so much, Kishore. We have some questions. Let me go in here. If you do have a question, you can go ahead and type that in your Q&A button. First question, what are the assumptions around the ejection of particles, and in parentheses, size, temperature, threshold of tolerance for exposure?
I showed several examples here.
Yeah, I think it was about halfway through your presentation based on the timestamp.
Yeah, those were gaseous.
Or maybe toward the end.
Yep. Yeah, those are gaseous contaminants. They were not particulates. So, but when the size of contaminants, the particulates, go below 5 micron, then they almost behave like gases. So what was the temperature? It was released at room temperature. These are all good parameters there. They go as an input to the analysis.
Okay. This is a question from the dental space. The question is, what would you recommend a dentist consider? Source control, right? But now there are extraoral devices like funnels and suction, or room purifiers placed at the foot of the patient's chair. So I guess it's kind of where you position any sort of air filtration.
I'm afraid I can't give you a generalized recommendation for this. Certainly, people are encouraged to employ these devices and techniques. As I said in my presentation, where is your supply in your room? Where the air is coming in? What type of diffuser there in your clinic? Is it a slot diffuser or a four-way diffuser? Where your return is there? Where the door of your clinic is, whether it is open or closed? All these things will matter, because simply putting a cleaning device in a place is not enough, as I said. So where to place that is also important to understand the airflow patterns. Okay.
Question, I think from the same space, dental. How would a dentist get a CFD analysis done?
There are a couple of ways of doing that. The easiest way is to find the expert who can do the analysis for you. Remember, this is not a push button technology. This is not a spreadsheet kind of simulation. The person who does the CFD should clearly have understanding of fluid mechanics, heat transfer, and of course, the science of computational fluid dynamics. So I would strongly recommend to find an expert who can do it for you, and not just do CFD, but provide you the guidance and recommendation. How can you mitigate the situation, or who can help you find the right device and where it should be placed in your clinic.
Okay. We can put, we'll put Kishore's contact information on the tips resource page. So if anyone wants to contact you, and you can point them in the right direction, or you could assist directly. I have a question here. Does bipolar ionization of supply air that reduces particles help reduce transmission of biological pathogens? So the question is specific to bipolar ionization of supply air. Do you have any comment on that? Have you seen data?
No, I don't have any comment on that one. My focus is more on airflow patterns and airflow movement and resulting flow pattern of contaminants. So they can find knowledge on ASHRAE webpage. I mean, we have on ASHRAE webpage, we have the pandemic task force and ton of information on ASHRAE's webpage. They can go there.
Okay. We'll do a couple more here, and if we don't get to your question, we'll get answers typed up and we'll post them on the TIPS resource page. It says, in your examples, you focus largely on mechanical ventilated spaces. Do you have any advice for improving ventilation effectiveness in naturally ventilated spaces?
Excellent question. When air moves into the space, it doesn't know whether it's mechanically ventilated or naturally ventilated. So in a naturally ventilated space, you have openings on the facade of your building, on your space, whether those are operable windows or louvers or whatever it is. That's where your air is coming in or going out. Basically, depending on the wind patterns around your building and wind direction and wind speed, some of these openings will act as supply and some of these openings will act as return or exhaust. So try to understand that. Again, cross ventilation is very popular. If you have the opposite side windows, just open those. It can move the air from one place to another. If you have very deep floor plate, more than 15 feet, remember that air that's coming in is not going to go away right away. It will take some circulation and wander in your space before it gets out. So again, the CFD analysis is not just limited to mechanically ventilated spaces. We can do simulations, and I have done several of those for naturally ventilated spaces.
Okay. Do you have a formula, or is there a formula to compute how many exhaust grills are needed per square footage of an area / space, and depending on the exposure to risk factors? Are there any?
Excellent question, and it's really intriguing to me. I think I should put this in my ASHRAE committee to write a research proposal on this one, to at least get an idea, if at all we can, or come up with guidance, how many exhaust grills I need. I'm afraid we may not be able to come up with a general guidance that may work for each and every space. Remember, that's where computational fluid dynamics comes into picture. Each space is unique. Their layout of furniture, their supply flow rates, where the supply is and return is, and we need to analyze that, put the microscope on your space and analyze and understand. Remember, we cannot solve a problem before understanding it. So we need to do the diagnosis first and then find the right solution. So I don't know if there is any formula like that.
Okay. You included an assessment of mitigation strategies if a dental office or a medical clinic wanted to, or even a hospital wanted to move forward with that. What would be the first steps of doing that?
The first step would be to lay out the space, find where your supply locations are, where your return locations are. That's the first step. How much air you are bringing in and at probably what temperature, correct? Second step is to find out how you laid out your clinic, where your dental chair is, where your cabinets are, do you have any other major obstructions to airflow, and try to understand how air might be moving. The third step would be performing computational fluid dynamics analysis after you gather all this information. Understand how the air is moving. Once we know the analysis, once we see the airflow pattern, then we can decide what would be the right strategy to keep the space clean.
Okay, great. And when we take this last question, is there any guideline to exhausting contaminated air outside, especially if exhausting at low levels where people outside might breathe it in?
No. Again, I will direct you to ASHRAE website.
Okay.
We have a technical committee on laboratory spaces, and they often talk about the height of the exhaust stacks and their diameter and the plume. We are not at that level. I mean, if you are just exhausting your room air out, if you are at the roof level, the wind around the roof will determine where your exhaust goes. If you are afraid that it is coming at the pedestrian level, then it needs to be thought through.
Okay. Well, great. Well, thank you so much. Great topic. I appreciate everyone for joining. As mentioned, we did record the event, so the recording will be posted at the TIPS website in the next couple days. We'll also publish the questions and answers along with Kishore's contact information if anyone wants to follow up with him.
My email address was there, and if I can share my screen just a minute.
Yeah. Yeah. Go ahead.
Those who want to note down my email address and phone number,
yep.
Feel free to contact me if you have any more questions.
Do you want to share your screen real quick?
Just a minute.
Yep.
Yeah.
There we go.
Can you see my screen, Dan?
Yep. Yeah, we see your website.
Yeah, and let me bring my last slide up.
You have your email at the.
Yeah. Can you
Perfect.
see my email address? Phone
yep.
number is there.
Yep.
Yeah. So people can note it down.
Very good. Well, thank you very much,
Okay.
Kishore, and everyone for joining, and look for additional webinars from TIPS moving forward. Everyone have a great day.
Thank you, Dan. Bye.